Hey guys, today we're going to look at Riemann sums. Now in calculus, when we look at an integral like this, what we looked at last class, this represents the antiderivative of a function, and it is also referred to as the indefinite integral. Now sometimes you'll see notation written like this, where you have the integral and then you'll have two numbers here at the top and the bottom of the integral. Now this represents the area of the region that is bounded by the curve of the function and the x-axis on the interval a to b, which is also called the definite integral. So indefinite does not have an interval, and definite does have an interval. And what it represents is the area underneath the curve. So you can see here, this is kind of like a picture of what I'm talking about. We have the integral on the interval a to b of f of x. This is my graph of f of x. This is x is equal to a. This is x is equal to b. So what this integral represents is the area that is bounded by your function and the x values as well as the x-axis. Now a Riemann sum is a way that we use to estimate the area that is underneath the curve. We will learn how to calculate four types of Riemann sums today: a left-hand sum, a right-hand sum, a midpoint, and a trapezoidal sum. So let's look at left-hand sums. Here we have the graph of the function f of x, and we want to use Riemann sums to estimate for this integral from -1 to 3. So our first x value is on the bottom, and then that's the start of the interval, and then the top number here is the end of the interval, just so you understand how this is read. So we want to estimate this using a Riemann sum with rectangles of length 2 units. So we're starting here at -1 and we're going to 3. Now what we do is we draw rectangles that have a length of 2 units. The x-axis rather, that is the length of the rectangle. So 2 units, that would be from -1 to 1. And because this is a left-hand sum, what we do is we place the upper left-hand vertex of the rectangle on the curve each time, meaning that on the left side here, this is the left side of my rectangle, the height is determined by the curve. So this would be my first rectangle. Then my second rectangle is the one that comes right after, so from 1 to 3. And the height of that rectangle, again, determined by the left side and the curve. So we would draw our rectangle here. So this is the area that we're trying to calculate. And this is going to estimate the area that is beneath the curve. Of course, we see that there are some empty spaces here, and that's okay because we have some over space here on this other side of this rectangle. Like I said, these Riemann sums are estimates. It's not going to give you an exact value. So if you want to estimate this, we would find the area of each rectangle. This rectangle here has a base of 2 and the height of 1. Plus this rectangle, which also has a base of 2, because they're all going to have a base of 2 since we are dividing these rectangles with a length of 2 units. And then the height is 5. So now we would add 2 plus 10. This gives me an estimate of 12. So that would be the area, or the estimate of the area for this function. Now we're going to repeat this process, but this time we're going to estimate the area using rectangles with a length of 1 unit. So I'm going to switch colors here so we can see those rectangles. So we're going to go from -1 to 3, but every rectangle will only be 1 unit. Again, the height is determined by the left side of each rectangle. This is my next rectangle. Sorry that they're not very clean. Then my next rectangle. And then our last rectangle here, which is determined by this height. So now these are the rectangles that I need to find the area for. So we have this one here, which is 1 times 1. plus this area here, which is 1 times 4, plus this one that's 1 times 5, and the last one, which is 1 times 4. Now, because these are all equal lengths, you could have also written this, and I mean, this goes for both this sum and this sum up here. You could have written this one, since they all have the same height, as 2 times 1 plus 5, because they all have that same height. And this is like saying 1 times 1 plus 4 plus 5 plus 4, which this one would equal to 1 plus 4 is 5, plus 5 is 10, plus 4 is 14. So now what is different about the area under the curve? Is it closer or farther area for what you think would be the exact area? As you can see from these rectangles, it covers more of the space beneath the curve. So in fact, this particular Riemann sum would be closer to the exact area than the one with a rectangle of length 2 units. So what does this tell us? This tells us that the smaller your rectangles, the more precise the area is going to be. Now we're going to look at a right Riemann sum. Now, a right Riemann sum is essentially the same thing as a left Riemann sum. It's just now you're using the right side of the rectangle to determine the height. So we're going to start with the same function. We have the interval from -1 to 3, and we're going to use a right Riemann sum with a length of 2 units. So here we go. We're starting at -1, 2 units. This is the right side. So this would be the rectangle that I would use. Then from 1 to 3, again, I'm using the right side. So then this is the rectangle I want to use. Now each one of these bases is 2. And then the height for the first rectangle is 5, plus the height of the second rectangle, which is 1. So this is a more efficient way of finding the Riemann sum. If the bases of all the rectangles are the same, you can just write that on the outside and then open parentheses and add all of the heights. So this is approximately 2 times 6, which gives me an estimate, again, of 12. And in this case, it's the same as the left Riemann sum because the function that we're looking at is symmetric. So whether you're doing a right or a left, you would get the same answer. Now let's repeat this, but using the area with only 1 unit. So here we go. We have our first rectangle here. We're using the right sum, so this would be the rectangle. Here's the next one. The height is now this rectangle. Then we have this next one. Again, I'm always using the right side to determine the height of my rectangle. My last rectangle here. Okay, so now, just so you understand a more precise way of writing these Riemann sums. We have the height of each, the base of each rectangle, which is 1. Then we would write the function values. So the height of this rectangle is here, which is the height of f of 0, plus the height of this rectangle, this is x is equal to 1, so f of 1, plus the next height, which is f of 2, plus the height of the last rectangle, which is f of 3. So then we would fill out those heights. So we have 1, f of 0 is 4, plus f of 1, which is 5, plus f of 2, which is 4, plus f of 3, which is 1. And now we add all of that together. So 1 times 4 plus 5 is 9, plus 4 is 13, plus 1 is 14, which gives me an estimate of 14. So this would be my Riemann sum. Now, do you notice anything about the leftover area of each Riemann sum based on the function's concavity and increasing, decreasing behavior? So something that you should notice, if you look for on this side of the graph, when for a right sum, we'll start with the right sum because we have it right here in front of us. When the function is increasing, the area will be over. Because you can see, since it's an increasing function, when we're using the right sum, we're using a lesser height. So the rectangle is going to go over the curve. But then on the other side, as it's decreasing, the area is under. And you can see that because the rectangles here are below the curve. Now, for the left sum, it's the opposite. And we'll look at the graph on the other side in a second. So first, let's look at when the function is increasing. See, on the left side, if you're using a left sum, when the function is increasing, those rectangles are below the curve. So that means that the area would be under. And when it's decreasing, it's the opposite. If you look back, when my function is decreasing, those rectangles are over the curve. So the area would be over. Now, in order to investigate what the concavity has to do with it, let's examine a couple of graphs. For each of these functions below, the left and right-hand sums were drawn in already. The red bars represent the right sum, and the blue bars represent the left sum. So when you have a function that is concave up, which is this first graph here, the left sum, which is the one in blue, is clearly under. And the right sum, which is the one in red, is over. So this is for when it's an increasing function and concave up. Now we're going to look at an increasing function and concave down. For a left sum, again, the left is the one in blue. It is under, because you can see that the rectangles are underneath the curve. But for the right sum, we have the red rectangles, which are over the curve. So the area will be over. So concavity doesn't seem to have anything to do with it, because as long as it's increasing, a left sum will be under and a right sum will be over. Let's see if it's the same thing for decreasing. For a decreasing function that is concave up, which is this third graph here, the left-hand sum, which is again the blue, is over because it's over the curve. So that has an area that is over. For the right hand, which is the red, it's underneath the curve. So this will be an under approximation for the area. For a left-hand sum, when it's concave down and decreasing, again the blue, we can see that it is over because it is on top of that function. But for the right hand, which is the one in red, it is underneath the curve. So concavity does not matter. As long as your function is increasing, the left sum will be an under approximation, and the right sum would be an over approximation. If your function is decreasing, it doesn't matter if it's concave up or concave down. The left sum will be an over approximation, and the right sum will be an under approximation. Now we're going to look at a midpoint Riemann sum. So here it says to estimate the value of the integral from -3 to 5 f of x dx using a midpoint Riemann sum and 4 subintervals of equal length. Here it does not tell you what the intervals of each of these rectangles should be. They just tell you 4 subintervals of equal length. So in order to figure out how many, what the length of each rectangle should be, you would use this formula here. So your change in x, that's what the triangle means, the change in x, would be the length of each rectangle. So what we do is we do b minus a. So this is your interval. Remember that this is a and this is b. And then we divide by the number of subintervals that they say. So my change in x would be 5 minus -3, so plus 3, divided by the 4 subintervals. So this is 8 divided by 4, so 2. So each rectangle is going to have a height of 2. So here we go. if we want to estimate this integral. Now let's write this the proper way. Each rectangle has an equal length, so we're going to say the 2 is my base. So I'm going to draw this in. So we have from -3 to 2, and we are using a midpoint sum. So the midpoint between -3 and -1 is -2. So we would use the function value for -2. So that is my first rectangle. My second rectangle will be from -1 to 1, and my midpoint between -1 and 1 is 0. So the next function value that I would add is f of 0. Now my next rectangle from 1 to 3, my midpoint is 2. So we would use f of 2 for the height. And finally 3 to 5, where my midpoint is 4. And that is my last rectangle. So we are using f of 4. So this is the proper way of writing your Riemann sums. You want to use, if you have equal subintervals, you would put the base of each rectangle on the outside, open a bracket or a parentheses, and then use the function notation to represent the heights of each one. So here we go. We have 2 times f of -2, which is 3, plus f of 0, which is 1, plus f of 2, which is 3, plus f of 4, which is 9. And now we work that out. So we have the 2 times 3 plus 1 is 4, plus 3 is 7, plus 9 is 16. And 2 times 16 gives me an approximate area of 32. So that's how you would figure out what those equal subintervals would be. Now lastly, the last Riemann sum we're going to look at is a trapezoidal sum. Now, a trapezoidal sum is probably one of the most accurate of the Riemann sums, simply because it's always going to lie right beneath the curve. Now, we have to know what is the area of a trapezoid, and this is the equation for the area of a trapezoid. It is 1/2 times the height times the base, the first base plus the second base. So, because remember, a trapezoid looks like this. So 1/2 times the height of the rectangle times b1 plus b2. So now let's see how we draw this in. We want to find the trapezoidal sum using 6 subintervals of equal length. So remember how we find equal length. We have our change in x, and that is b minus a divided by the subintervals. So here we have 2 minus 4 minus -4, so that would be our change in x. 2 minus -4 is 2 plus 4 divided by 6. So the height of each rectangle is going to be 1. So we're starting at -4, and then we're going to 3, to 2, to 1, to 0, to 1. Sorry, from -4 to -3, -2, etc. Okay, so let's draw them in, and then we'll figure out what to write inside here. So we have here, this is my height, or rather my base, and this is my other base, because these trapezoids are on their side. So you can see here that this is base 1, and this is base 2. For the second trapezoid, this would be base 1, and this would be base 2. For my other trapezoid, base 1, base 2. Same thing all the way across. Ooh, this is hard to see. I think it's yes, 5. Right here. Oh, and then I missed this one, which is up here. So you can see how this Riemann sum here is super close to my curve here, and it gives us a very accurate picture of what the area could be. Now, how would we write this out? So for each trapezoid, right, we have to add base 1 plus base 2. And then we have the height here, Oh, and I forgot about the 1/2. So it's 1 times 1/2. So we'll just write 1/2, right? Because the area of a trapezoid is 1/2 times the height. So my first base is f of -4 plus f of -3, because that is my first trapezoid. Now my second trapezoid is f of -3 again plus f of -2. So I'm going to repeat f of -3, so I can just put 2 because I'm going to add another f of -3 plus, now I'm going to put 2 f of -2, and this is because at -2, that's the base for this trapezoid as well as another base for this trapezoid. So when you're writing your trapezoidal sum, basically you have the first height, which is only once, and then all of the heights afterwards and in between are twice because it's going to repeat for every single trapezoid except for the last. So once for the first, double for all of them except for the last one here. So I'm going to add 2 of f of -1 plus 2 f of 0 plus 2 f of 1 plus f of 2, since that is my last height that does not repeat. So now I'm going to write out all of these heights. So my area is going to estimate to be 1/2 times f of -4, which is 10, plus 2 times f of -3, which is 5, so 10, plus 2 of f of -2, which is 2, so 2 times 2 is 4, plus 2 f of -1, which is 1, so 2 times 1 is 2, plus 2 times f of 0, which is 2, so 4, plus 2 f of 1, which is 5, so 10, plus f of 2, which is 10. And now we add all of this together. So this is 1/2, and then we have 10 plus 10 is 20, plus 4 is 24, plus 2, 26, plus 4, 30, plus 10 is 40, plus 10 is 50. And half of 50 is approximately 25. So that would be the area using the trapezoidal sum of 1 unit. Now we're going to do the same thing, but for this parabola facing downwards. So we have 2, -1, from -4 to 2. My change in x for this is the same thing, so 1. So we have our formula here, which is 1/2 times the height, which is 1, which I don't need to write. And then let's draw these in. So we're starting at -4 to 3 to -2 to 1 to 0, 1, and 2. So let's draw these trapezoids. This height is just 0, so it's going to actually be more of a triangle. Then we have the next one here. Then we have this one here. Then this one. And the last one, which is kind of like a triangle. Okay, so we would write out what we got here, like with function notation. So the first height is f of -4 plus 2 f of -3 plus 2 f of -2 plus 2 f of -1 plus 2 f of 0 plus 2 f of 1, and then the last one, which is f of 2, does not repeat. So this is for my trapezoidal sum, and now we are going to plug in those function values. So 1/2, f of -4 is 0, plus 2 f of -3, which is 5, so 2 times 5 is 10, plus 2 f of -2, which is 8, so 16, plus 2 f of negative 2, f of negative 1, which is 9, so 9 times 2 is 18, plus 2 f of 0, which is 8, so 2 times 8 is 16, plus 2 f of 1, which is 5, so 2 times 5 is 10, plus f of 0, which is, f of 2, which is 0. And now we add and find that final answer. So 1/2 times 10 plus 16 is 26. 26 plus 18 is 44. Plus 16 is 60. Plus 10 is 70. And half of 70 is approximately 35. Now for this one, what do you notice about the underage overage of areas of the trapezoidal sums based on the function's concavity? Now it's kind of hard to see because I know that my rectangles are not drawn very precisely, but you can see, not my rectangles, my trapezoids, but you can see that these trapezoids here are more over the curve than these here. These are under the curve. You can see that there's spaces right underneath. So when you have a function that is concave up, a trapezoidal sum would be an overestimate. And when it is concave down, the trapezoidal sum would be an underestimate. Now that we've covered all four of the types of Riemann sums, let's look at how we would apply Riemann sums using charts. So for this first one, it says to approximate the integral from 0 to 25 of f of x dx using a midpoint sum and 3 subintervals. So I got to find a way of taking this chart and dividing it into 3 parts. So since this is a midpoint sum, that means that we're going to need a value in the middle between 2 points. So I'm going to try dividing it like this. Maybe from 0 to 7, and then from 7 to 15, and then from 15 to 25. And that actually does give me 3 subintervals. So this works. So the thing with charts is you can only use the values that is given to you. You may not have equal bases for each rectangle, and that's okay. So let's see how we can write this out. So when you're setting up your Riemann sum, you set up your integral here of f of x dx. Remember that this is an approximation, so please use the approximation symbol. For our first height here, or base, the bases, remember, are determined by the x's, and it's a change in the x. So from 0 to 7, we have a base of 7. And then from 7 to 15, we have a base of 8. So that means that all of these rectangles here will have different bases. So we can't just put the base here and then open the bracket and put the function values. We got to do each one separately. So my first rectangle has a base of 7. And since we're using the midpoint, we are using f of 4 because it is between 0 and 7. The next rectangle from 7 to 15, the base is 8, and we got to use the midpoint, so f of 12. Plus, the next one is from 15 to 25, so that base is 10, and we're using the midpoint, so f of 20. And now we plug in those numbers. So 7 times f of 4, which is 6, plus 8 times f of 2, which is negative 10. Plus 10 times f of 20, which is 8. So we get here 42 minus 80 plus 80. The 80s will cancel, and we're left with an approximation of 42. So this would be my area. Now let's look at the next one. Approximate the integral from 0 to 15 of f of x dx using a left-hand sum and 4 subintervals. So you got to pay attention to the interval that's given. It's only from 0 to 15, and we're given the same exact chart. So we don't need these values because this is 20 and 25, which is outside of my interval. Since we want 4 subintervals, that means that we can divide our chart here into 4 parts. So it would be from 0 to 4, 4 to 7, 7 to 12, and 12 to 15. We are using a left-hand sum, so that means that we would start with f of 0 for the left side of my rectangle. Then for this rectangle, it would be f of 4. Then for this rectangle, it would be f of 7. And for the last rectangle, it would be f of 12. So if you're using a left-hand sum, you are using all of the values of f of x except for the last one because you're starting on the left side. So here we go. My integral from 0 to 15 of f of x dx is approximately, now this first rectangle from 0 to 4 has a base of 4, and we're using the height of f of 0. Plus, my second rectangle from 4 to 7 has a base of 3, and we're using the value of f of 4. Plus, from 7 to 12, my base here is 5, and we're using the value of f of 7. And for the last rectangle from 12 to 15, the base is the base is 3, and we're using the height of f of 12. Now we're going to plug in those values. So 4 times f of 0, which is 15, plus 3 times f of 4, which is 6, plus 5 times f of 7, which is negative 5, plus 3 f of 12, which is negative 10. And now we multiply and add all of this together. 4 times 15 is 60, plus 18, minus 25, minus 30. 60 plus 18 is 78. 78 minus 25 is 53, and 53 minus 30 is 23. So my area is approximately 23. Now let's try that here. We are approximating the integral from 4 to 20 of f of x dx using a right-hand sum and 4 subintervals. So we're going from 4 to 20, so that means I can disregard 0 and 25. 4 subintervals, so I'm going to divide this from 4 to 7, 7 to 12, 12 to 15, and 15 to 20. So let's see if we can write this out. We have here the integral from 4 to 20 of f of x dx is approximately, now we're going from 4 to 7, so my base is 3, and I need to use the right sum, so f of 7, plus my second rectangle from 7 to 12 has a base of 5, and we're using the height of f of 12, plus the base from 12 to 15 is 3, and we're using the height of the right side, which is f of 15, plus from 15 to 20 is 5, and we're using the height of f of 20. So what you'll notice here is for a left sum, we used all of the values except for the last because we're starting on the left side. And then for a right sum, we're using all of the values instead of the first because we're looking at the right side. So left values, right values. And now we just plug in those values and sum it all up. So 3 times f of 7, which is negative 5, plus 5 f of 12, which is negative 10, plus 3 f of 15, which is negative 2, plus 5 f of 20, which is 8. So we get here, this is negative 15 minus 50 minus 6 plus 40. Negative 15 minus 50 is negative 65, minus 6 is negative 71, plus 40, we get an approximate area of negative 31. Now you're probably wondering, how can we get a negative area? Now, the way that this works, and we'll examine this a lot more later, but the way that you get a negative area is if the function is below the x-axis. So that area would be considered negative. And again, we'll examine that later on. Now we're going to use this last one here, approximate the area for 0 to 25 of f of x dx using a trapezoidal sum and 3 subintervals. So we want to divide from 0 to 25 into 3 parts, which we did up here. So we're going to go from 0 to 7, 7 to 15, and 15 to 25. If you're doing a trapezoidal sum, remember you got to keep in mind the area of a trapezoid, which is 1/2 times the height times base 1 plus base 2. So for our trapezoids here, the change in the x is not the base, it's actually the height of those trapezoids. So we're going to set this up. The integral from 0 to 25 of f of x dx is going to be approximately, now all of these have different bases, different heights. So we got to do each one separately. So we're going to have the 1/2 on the outside because they're all going to get multiplied by 1/2. The height of my first trapezoid is from 0 to 7, so 7. And then we would use the function values for f of 0 and f of 7, since those would be our bases. So f of 0 plus f of 7. Now we're going to go to the next trapezoid. From 7 to 15, the height is 8. And we're going to use the bases, which is f of 7 and f of 15. Plus our final trapezoid here from 15 to 25, the height would be 10. And we're using the bases of the endpoints here, so f of 15 plus f of 25. So now let's put all of this together, plugging in those values. We have 1/2 times 7 times f of 0, which is 15, plus f of 7, which is -5, so 10. Plus 8 times f of 7 plus f of 15. So -5 plus -2 is -7. Plus our final trapezoid, which has the height of 10, f of 15 plus f of 25, so -2 plus 20, which is 18. So we have 1/2. This is 70 minus 56 plus 180. (70 minus 56 plus 180 is 194. And 194 divided by 1/2 is 97. And so this would be my approximate area. Now we're going to look at how to calculate Riemann sums from a function's equation. Now calculating a Riemann sums from a function's equation is tricky because you have to be able to visualize what the rectangles and trapezoids would look like on your graph and their dimensions. So you have to be sure to keep track of those function values. Now these two questions are calculator active. So I'm going to be using the calculator here and hopefully walking you through how this would work. So we want to approximate the area under the graph of f of theta is equal to sine of theta over 2 on the interval 0 to 2 pi using a midpoint Riemann sum and 4 equal subdivisions. So since we have 4 equal subdivisions, we need to know what the change in x would be. So that way I know what the base of each rectangle would be. So remember that change in x is calculated by finding b minus a divided by the number of subdivisions. So this is our interval. So 0 to 2 pi. So this is a and this is b. So 2 pi minus 0 divided by the 4 subdivisions, which gives me pi over 2. So that means that the base of each rectangle is going to be pi over 2. So let's start setting up our integral here. We are estimating from 0 to 2 pi of f of theta Now, since my variable is theta, then this would be d theta. And that is going to be approximately, my base for each rectangle is pi over 2. Now, how do we know what heights we're going to use? Well, if we're starting at 0 and we're going to 2 pi, and every rectangle is pi over 2, we need a midpoint. So the midpoint, like the first rectangle, is from 0 to pi over 2. So we need the midpoint between 0 and pi over 2. So what you do to find a midpoint is you add 0 plus pi over 2, and then you divide by 2 to give you the middle, which pi over 2 divided by 2 is the same thing as pi over 2 times 1/2, which is pi over 4. So that would be our first function value, f of pi over 4. Now you don't have to do this to get the rest of them. We know that the x's change by every pi over 2. So that means that the midpoints will also go by pi over 2, since all of the rectangles are the same subdivisions. So we're going to add pi over 2 to pi over 4 to get the next function value, which meaning we would add 2 pi over 4. So that way we can actually be able to add until we get to the end of our interval here. So I'm going to write this here. I'm adding 2 pi over 4 to every f of theta. So 2 pi over 4 plus f of pi over 4 would be f of 3 pi over 4. That would be my very next midpoint. Because again, remember that your rectangles are every pi over 2. So my midpoint is also going to be every pi over 2. So that's why I'm adding 2 pi over 4. Since our first midpoint is pi over 4, I need to add pi over 2, which the equivalent is the 2 pi over 4. So I'm going to add another f of 3 pi over 4 plus 2 pi over 4 is 5 pi over 4 plus f of 7 pi over 4. If I were to keep adding, right, the 2 pi over 4, I would get 9 pi over 4, which is more than 2 pi. So this is the end of my interval. Again, it also tells us 4 equal subdivisions, meaning we would have 4 rectangles. So I have 4 function values. So here we go. We have pi over 2. Now I need to know what these function values are, and that's what the calculator comes in. So I'm going to go to my calculator, and I'm going to graph the function. So sine of x divided by 2. And let's graph it. Well, let's adjust the window from 0 to 2 pi. Now let's get those function values. So we go to second calc. I want my value of pi divided by 4, which is 0.3826. So that's my first value. Plus, now I want the value for 3 pi over 4. So 3 pi over 4, which gives us 0.9238. Plus, now I want 5 pi over 4. Which is the same value, 0.9238. And the last one I want is 7 pi over 4. Which is 0.3826. So now I'm going to add all of this together and then multiply by pi over 2 to get our final answer. So let's go ahead and do that. I'm going to just quit here. So 0.3826 plus 0.9238 plus 0.9238 plus 0.3826, which gives me 2.6128, and now I'm going to multiply by pi divided by 2. which gives me 4.1041. And that is my approximate area. Now, let's look at this next example. Estimate the value of the integral from 0 to 2 of 2 to the x plus 3 dx using a trapezoidal sum with 4 equal subdivisions. So again, I need to know what my change in x is. We're going to do b minus a, so 2 minus 0, which is 2, divided by 4 equal subdivisions, which gives me 1/2. So that means that every trapezoid will have a height of 1/2. So let's start setting up our integral. It's from 0 to 2 of 2 raised to the x plus 3 dx is going to be approximately, remember the area of a trapezoid is 1/2 times the height, which is also 1/2. Now in this particular case, since it's 4 equal subdivisions, we use the first function value, which is f of 0, because that's the beginning of our interval, plus then we're going to add double of every one of those intervals in between, and the last one is singular. So our equal subdivisions is 1/2, so that means that the bases are every 1/2 unit. So my next base would be 2 f of 1/2, and then I keep adding 1/2 to those x values. So plus 2 f of 1 plus 2 f of 3 over 2, or 1.5, whatever you prefer to write. And then 2 is my last interval, or my last number here, because it's my last function value, because it's the endpoint of the interval. So I do not double it, it'll be f of 2. Because remember that the trapezoids all share the bases in the middle except for the first and the last. Once you have it set up, that's the hardest part. The rest is just using the calculator to get these function values. So let's work this out. 1/2 times 1/2 is 1 over 4. Now I want to know what is f of 0. So I'm going to go to my calculator here. Let's graph this function. So 2 raised to the x plus 3. And I'm going to adjust my interval here so that it's from 0 to 2. Now let's start getting these function values. So I want to go to my value here. So I want first 0, which is 4, plus 2 f of 1/2. So let's just put 0.5, which is 4.142, plus 2 f of 1, which is 5, plus 2 f of 3 over 2, or 1.5, which is 5.8284, plus finally f of 2, which is 7. So now we're going to add all of this together. So 1 over 4, we have 4, I'm going to add these already because they're easy to add. 4 plus 7 is 11. So I'm done with these. Let's do 2 times 4.1, that would just be 8.284, plus 10, plus, let's do 2 times that, let's quit. 2 times 5.8, 8284, which is 11.6568. Let's add all of that up. So we have 11 plus 8.284 plus 10 plus 11.6568, which gives me 40.9408. And then we have to divide that by 4. And we get 10.23, what was that? 52. And that would be my trapezoidal sum. Okay, we're almost there. We're going to look at some applications. And these are like examples of what you might see in an FRQ. It says here, the table below represents the velocity in feet per second of a car traveling on a straight road over a 50-second time interval. Estimate the total distance traveled by the car using a left-hand sum with 5 intervals of equal length. So as you can see, all of these seconds here, they go by 5. So they are all equal length, but we want 5 sub-intervals. So we got to find a way of perhaps dividing this chart here by 5. Obviously, you can't go from 0 to 5, 5 to 10, because that's going to be more than 5. So let's try 0 to 10, 10 to 20, 20 to 30, 30 to 40, and 40 to 50. And that does give me those 5 sub-intervals. You could have also done b minus a divided by 5, right? 50 minus 0 divided by 5 is 10, so it's every 10. That would have worked out as well. So if we want the right sum here, we're going to estimate. So this is from 0 to 50 of v of t dt. Each rectangle has a base of 10. And then since we are using a left-hand sum, we start with f of 0, and we use all of the function values except for f of 50 because it's the last one. So f of 0 plus f of 10 plus f of 20 plus f of 30 plus f of 40. Since remember, it's the left side of every rectangle. And now we plug in those function values. So 10 times f of 0, which is 0, plus f of 10, which is 20, plus f of 20, which is 52, plus f of 30, which is 80, plus f of 40, which is 77. If you were to add all of these numbers together, we would get 10 times 229. And 10 times 229 is 2,290. Now, we integrated velocity. So that means that what I just found is position of the function. So we have to make sure that we include our units. Since this is position, our units would be the unit of length, which is feet. Now here, estimate the total distance traveled by the car using a right-hand sum with 5 subintervals of equal length. So this is exactly the same intervals because we've already divided it into 5, but now we're using a right-hand sum. So that means that we're going to use the right side of all of these rectangles. So we would start with f of 10 and then use f of 20, 30, 40, and 50 because we're using all of the right-hand sums. So we're estimating from 0 to 50 of v of t dt. Each interval is 10 units. So we're using, again, f of 10 plus f of 20 plus f of 30 plus f of 40 plus f of 50. Now we're going to plug in those values. So 10 times f of 10, which is 20, plus f of 20, which is 52, plus f of 30, which is 80, plus f of 40, which is 77, plus f of 50, which is 74. If you add all of those numbers together, you would get 303. So my final answer would be 3,030 feet. Because again, we're estimating the total distance that was traveled, which is the position. Now we have estimate the total distance traveled by the car using a trapezoidal sum with 5 intervals of equal length. So again, these are still 5 intervals of equal length, but now this is a trapezoidal sum. So when we're doing a trapezoidal sum, remember your formula here. So 0 to 50 of v of t dt is going to be approximately 1/2 times the height of each trapezoid, which is still 10. And then since these are equal subintervals, we use the first one once, and then, because remember, this is base 1, base 2, then base 1, base 2, base 1, base 2. Those middle bases all repeat twice, so that's why we're doing that 2 f of 10, 2 f of 20, etc. So f of 0 is only used once, plus 2 f of 10, plus 2 f of 20, plus 2 f of 30, plus 2 f of 40, plus f of 50 only once. Now we plug in those function values. Half of 10 is 5, f of 0 is 0, plus 2 f of 20, f of 10, which is 20, so 2 times 20 is 40, plus 2 f of 20, so twice of 52 is 104, plus 2 f of 30, so 80 times 2 is 160, plus 2 f of 40, which is 77, which is 2 times 77 is 154, plus f of 50, which is 74. When you add up all of these numbers, you will get 5 times 532. And when you multiply that together, 5 times 532 is 2,660. And again, this is feet. Okay, so it says here to find the average of the left and right sum, and how does this compare to the trapezoidal sum? So to find an average, you would add it up and then divide by how many numbers you're adding. We are just finding the average between the left and the right sum. So I would add those two together. So 2,290 plus 3,030, and I would divide that by 2. 2,290 plus 3,030 gives you 5,320. And when we divide that by 2, we get, I don't know why this is equals, this is not an approximation. And we get 2,660, which is the same as the trapezoidal sum. So that's the thing. If you're using a trapezoidal sum, if and only if those intervals are of equal length, it is equal to the average of the left and the right sum. Let's try one more. This first one is non-calculator. It says the table below shows the rate at which gas is leaking from a punctured gas tank in liters per minute. Use a left-hand sum of 4 rectangles to estimate the total number of liters that have leaked from the tank. So whenever we integrate something, which you'll notice, gives us, when we're integrating a rate, the answer is the amount of something. So since we are integrating a rate here and the rate of liters per minute, when we integrate it, that gives us the amount of liters that have leaked. So let's see how we can work this out. How should we divide this? We're using a left-hand sum. It doesn't tell us by how many subintervals, so we're just going to use every single one. So we're going to use 4 intervals. So we're going to integrate, and this is 0 to 5.5 because that is everything that is given in the table of we're going to call this R of t. And we're using a left-hand sum. So these here do not have equal lengths in the change in the t values. So we have to do each rectangle separately rather than writing the equal length on the outside because it's not equal. So this first rectangle has a base of 1.3. And we are using the function value. This is for a left-hand sum. So we're using the function value for r of 0. Plus. Now from 1.3 to 2.4 is 1.1. And we're going to use r of 1.3. I don't know why I put a parentheses there. Plus, now from 2.4 to 3.7, it increased by 1.3. And we're going to use r of 2.4. Plus, from 3.7 to 5.5 is a base of 1.8, and we are using r of 3.7. So now let's plug in these values. 1.3 times r of 0, which is 5.7, plus 1.1 times r of 1.3, which is 4.3, plus 1.3 times r of 2.4, which is 3.2. And last one, 1.8 times r of 3.7, which is 2.4. So now we are just going to use the calculator to multiply all of these out just to save on time. 1.3 times 5.7 is 7.41, plus 1.1 times 4.3 is 4.73, plus 1.3 times 3.2 is 4.16, plus 1.8 plus times 2.4 is 4.32. So now we're going to add all of that up. So 7.41 plus 4.73 plus 4.16 plus 4.32, which is 20.62. And remember our units here. We are estimating the total number of liters that have leaked from the tank. So 20.62 liters. Last question is a calculator question. A 30-gallon aquarium is being filled with water at a rate modeled by r of t is equal to 6 sine of pi over 8 t, where t is the time in minutes, and r of t is gallons per minute. Estimate how much water is in the tank after 5 minutes using a right-hand sum of 5 rectangles of equal length. So we want we want to estimate how much water is going in after 5 minutes. So that means that our interval is from 0 to 5 because of the 5 minutes. This is the function r of t dt. If it's equal subintervals of 5, that means that 5 minus 0 divided by 5 is 1. So the base of all of these rectangles will be 1. And now that means that the function values we're going to use is for the right-hand sum. So we're not going to start at 0, right, because that would be the left sum. We would start using f of 1. And then we're going to add 1 until we get to the end of our interval. So f of 2 plus f of 3 plus f of 4 plus f of 5. Now let's go ahead to our calculator. Let's graph that function and get those function values. So we are graphing 6 sine of pi over 8t. 6 sine pi, I'm going to put pi x over 8, which is the same thing. Okay, and let's adjust our window to reflect the interval, which is 5. So let's get f of 1, which is 2.2961. So 1 times 2.2961 plus, now let's do 2, which is 4.2426 plus f of 3, which is 5.5432 plus f of 4, which is 6, and finally f of 5, which is 5.5432. Now we're going to add all of that together. So 2.2961 plus 4.2426 plus 5.5432 plus 6 plus 5.5432. And we end up with a final value of 23.6251. And remember, here we are estimating how much water is in the tank, and it tells us that it's a 30-gallon tank. It's gallons per minute, so this should be gallons. And that's Riemann sums.